Okay, so good evening everyone. Welcome back to your 10th discussion session in Mechanical Behaviour of Materials. I'm Pragyandipta Mishra, Research Scholar from Department of Applied Mechanics and Biomedical Engineering at IIT Madras. So, in the last class we talked about various strengthening mechanisms in any material systems, right? How can we strengthen a material by using dislocations to our advantage? So we talked about how to do it using precipitate strengthening and dispersion strengthening. Today we'll be continuing the discussion and talking about two more strengthening mechanisms, basically the solid solution strengthening and grain boundary strengthening. Okay. So with that introduction out of the way, let's begin our session. So let's start with solid solution strengthening. Okay. So what exactly is the solid solution strengthening? So from the name itself you can guess, right? Now, if in precipitate strengthening, the strengthening was due to the presence of precipitate atoms. Here, the strengthening is due to the presence of solid atoms in the solution, right? So the strengthening due to addition of solid atoms is known as solid solution strengthening. Okay. Solid, or we can also say solute. Okay, solute atoms to the solution is called solid solution strengthening. Okay. So essentially what is happening is you are adding some sort of solute atoms into some solution, some matrix, and due to the presence of those solid atoms, you will see some sort of strengthening happening. Okay. Now then the obvious question that will arise is, we did the same thing while doing precipitate strengthening, right? Like we added some certain elements or like some atoms into the solution, and because of that we saw formation of precipitate phases which causes strengthening. So how are these two different, right? Essentially, solid solution strengthening and precipitate strengthening kind of have a similar starting point, right? You have a matrix and you start adding solute atoms to it, and in the process you either get a solid solution or you get a precipitate, right? What they differ is in whether you are adding the solute atom within the solubility limit. Okay, so there is something very important known as solubility limit that I discussed in the last class as well, right? So if you are adding well within the solubility limit, essentially you will get solid solution strengthening because the solute atoms will not cross the threshold. Okay, some threshold beyond which they are not able to dissolve anymore. So the solid atom will keep dissolving in the solution, in the process forming an alloy kind of system, right? So this alloy kind of system essentially is your solid solution, okay, and that causes strengthening. So the solid atoms will be present throughout the system, and they will cause strengthening at every place equally, right? On the other hand, precipitate strengthening, what happens is essentially you add beyond the solubility limit, and because you're adding beyond that solubility limit, over time the precipitate will start to the solid atom will kind of exceed the solubility limit, and then it has to come out in some one or the other form. So what it will do is it will try to mix up with the matrix atoms in some way or the other and come out as a separate phase. Okay, so that separate phase should be stable, of course. Like that goes without saying. If it is not stable, then it will not form. But a stable precipitate phase comes out, and that causes precipitate strengthening. Okay, so that is the essential difference. You see a separate phase formation in precipitate strengthening, whereas here you see a continuous phase. Like you don't see any a new phase coming out. The entire system is now a continuous phase. Okay, so if you see like the hardness versus aging time graph, like if you remember what we had drawn in the last class for precipitate strengthening, hardness versus aging time, there was this kind of graph, right? Right. So this progression in the graph, right? This progression from t is equal to 0 to some aging time, this progression is defined by precipitate strengthening, right? So the change in hardness with aging time is defined by precipitate strengthening. Then what does solid solution strengthening define? What do we get from solid solution strengthening in that scenario? We get this H naught, right? So initial hardness that we are getting, that H naught is coming through this solid solution strengthening. Okay, so this H naught is essentially defined by your solid solution strengthening. What kind of solutes are present will define how high or low this H naught is. Okay, so this is the contribution. Contribution of solid solution strengthening contribution of solid solution strengthening in contribution of solid solution strengthening in the hardness, okay, of a given system. Essentially, you can say that, of course, like this H naught is not only dependent on the solid solution strengthening, the solute atoms. It is dependent on a variety of factors, but the solute atoms will also influence how high or low this H naught value is. Okay, so that is the contribution of solid solution strengthening. So yeah, so what were the differences that we talked about? Let's write that down between precipitate strengthening and solid solution strengthening. First things, in solid solution strengthening, the crystal structure of the solvent will remain the same. Okay, like I said, there is no formation of a separate phase. Okay, in solid solution, the crystal structure of the solvent remains the same. Okay, in solid solution strengthening, solid solution essentially, not strengthening. Let's say just say that's the thing that is formed after you add solid atoms to the solution is solid solution. So solid solution, you'll see that the crystal structure of the solvent will remain the same. There is no change in the essential crystal structure. The solid atoms will just go and occupy spaces in between. We'll come back to that in some time. But yeah, essentially the crystal structure will not change. But precipitates will have like like can have very different crystal structure. Okay. Okay. Secondly, these solutes that we are adding, like, are atoms essentially. They are not like a separate phase. While precipitate is like a separate phase. Okay, so that is another important point that you can. Solutes are atoms, while precipitates okay. But precipitate is a phase. Okay, solutes are atoms, while precipitate is a phase. Okay. So I think we are clear on what is the difference between precipitate sending and solid solution sending now. Okay. So now let's understand how this solute concentration, how difference in solute concentration will like cause an effect in the strengthening, right, of this any alloy system. How changes in the solute concentration will cause a change in the strengthening behavior. Okay. Effect of solute concentration. Okay. So let's understand it with a stress strain curve. Okay. So let's draw this. Stress versus strain. Okay. So you have your general pure metal, which looks something like this. Just got a little bit. Right. So this is pure metal. Now let's draw a different ink problem. For addition of solute atoms, so you're adding solute to some concentration, let's say C1. Okay. So you'll see something like this. So till here it is the same. Then you will see this. It will go high, but it will end earlier. Okay. So this is C1 solute concentration. Let's use a different ink. Then you'll see another one which is something like this. If I add beyond that, it will be like C2. Okay, let's make C1 a little bit longer. Okay, so that you can clearly demarcate C1 and C2 where it is ending. So this is C2. So what you're seeing is C2 concentration essentially is higher than C1 concentration. Okay. So what are we noticing? Like what is the important thing that we are noticing? We are seeing that with increase in the solute concentration, the strength, the maximum value of stress, right? The maximum value of stress keeps moving up. That is, the strength will keep increasing, right? But also, you can see that ductility is decreasing, right? The length of the plastic region is decreasing, right? So here it was this long. Now it is this long in C1, and then in C2 again it's even lesser. So ductility keeps decreasing with increase in solute concentration, while the strength keeps increasing, right? So this is something that we have to understand, because while making decisions about increasing strength using solute concentration, you have to also understand that ductility is something that you're compromising on. So in order to find the right balance, you have to ensure that you need some specific strength and some specific ductility. You have to add solute in that particular ratio, which can give you that strength and ductility. Okay, so that's how you have to balance it out. Okay, so let's write it down. As we increase concentration, the solute concentration, the solute concentration strength increases and ductility decreases. So that's the first point. Strength increases and ductility decreases. Right. Why? Why do we see this strength increase? Essentially, that is the question, right? Why are we seeing this? Most obvious answer, the same answer that we have been giving for every strengthening mechanism. Essentially, this solid solution is offering a greater resistance to dislocation motion, right? Solid solution offers a greater resistance to the dislocation motion. Right? That is the essential reason why increasing the solute concentration would essentially strengthen the alloy, because you're seeing more and more resistance to dislocation motion. Okay. So if we plot it out in like a graph, how these how the strength and elongation varies with increase in solute concentration, it will look something like this. So let's say this is theoretical strength versus here we have A, complete 100% A, and weight percent of B is increasing as we go from left to right, okay, in the x-axis. Here we are plotting just a second. Yeah. On the second graph, we are plotting elongation versus again weight percent B increasing on this side. This is A. Okay. So theoretical strength, as we saw, will keep increasing with increase in solid concentration. Okay. So you'll see an increase. Okay. It might be linear, might not be linear, but essentially you will see an increase. Okay. That is what you have to concentrate about. Don't worry about whether it's linear or not. It's just understanding that it increases over time. Okay. We are just drawing it there. And elongation, on the other hand, we will see a continuous decrease. Again, it might not be linear. You might get some like slopey curve or something. But either ways, it will keep decreasing. Okay. The elongation that it can go. Okay. How much you can pull, how much ductile it is, will keep decreasing as the weight percent increases. Okay. Okay. So now let's come. Let's talk about what are the different types of solid solution that we can see. Okay. How do we distinguish between solid solutions? Okay. So it's divided into two halves. Substitutional solid solution and interstitial solid solution. Okay. Just a second. substitutional solid solution and interstitial solid solution. Okay. So, what are the essential differences? From the name itself, you can guess to an extent, right? In substitutional solid solution, what will happen? Interstitial solid solution, what will happen? So, what can we say? In substitution solid solution, solute atom replaces the solvent atoms, okay? Because it substitutes, that's the word, right? Substitutes. Solute atoms replace solvent atoms. By interstitial solid solution, what will happen? There's no replacement. Rather, solute atom will occupy voids or interstitial positions. Okay? Solute atoms occupy the voids or interstitial positions. Okay, so let's see. Let's represent it in form of a diagram. Okay, so let's say that this is my A atom. A is basically my solvent atom. Okay, inside it in bracket, this is solvent. And then let's use a different ink. Let's say this is my B atom, which is the solute. So essentially in substitutional, we'll have something like this is my crystal structure. Then what will happen is probably one of the atoms is getting substituted by a new atom. Okay, so essentially let's say this atom is getting substituted. So now instead of A, I have one substitutional atom B in between. Okay, so one example for this could be like nickel added to copper. Okay, so copper is my A atom, nickel is my B atom, nickel getting added to copper could be one good example. Okay, while in the interstitial case, how does that happen? So if we have a similar crystal structure, let's say like this. So here, the interstitial atom or the solute atom basically will be in the interstitial position. So it will be like somewhere here, might be somewhere here. So like this, it might occupy positions in between the atoms. Okay, so interstitial positions. Interstitial. Okay. So this is how an interstitial setup would look like. Okay. So a good example for this is carbon in iron. Okay. Okay. So now that you have understood what are the types, let's understand what kind of distortion we see in lattice due to the solute atoms. Okay. Because essentially that distortion is what will set up some sort of stress field that will affect the dislocation motion, right? So we need to understand what kind of distortions we'll see. Okay. So let's start with interstitial atom, interstitial solid atom. Okay. So let's redraw this, something like this again. So let's say I have a interstitial atom somewhere here. Okay. Let me use a different ink. So this is where an interstitial atom is present. Let's extend it a little bit more. Okay. So what kind of distortion field will we expect around this region? We'll see some sort of distortion like this. Okay. So we'll see some sort of like spread out distortion which is non-spherical. Okay. This is what an interstitial solid atom distortion field would look like. Okay. It will be spread out in one particular manner. Okay. On the other hand, if we see a substitution solid atom, so there will be two types of substitution solid atom that you can have, right? One which is bigger, the substitutional solute is bigger than the solvent, and one where it is smaller. Okay, so let's see both the cases. First case where it is bigger. Let me just redraw this one. So this is my solid atom, the shaded one in red. And then we can also have some sort of setup where it is smaller. So then the other atoms around it will try to like compress and come inside. So in both the cases, what kind of distortion field we will see? So here, what the distortion field would look something like this. You'll see some sort of similar distortion field like before in interstitial, but then you will also have distortion field in the going vertically as well. So it will be spherical. Here also it will be spherical, but in the opposite way. It will be like this, like this, like this, and like this. Okay. So essentially, what we can write is that in interstitial solute atom. Okay. Interstitial solute atom will lead to a non-spherical distortion field. While substitutional solute atom will lead to a spherical distortion. The stress field, essentially, so why are we talking about this? Like, what is the need for us to understand what kind of distortion field we are seeing around? So what is happening is the stress field around the solute atoms will interact with the stress fields around the dislocation, and because of this interaction, there will be hindrance in the motion of dislocation. Okay? So that will essentially lead to the strengthening. Okay, so let's write that down. The stress field around a dislocation atom. Sorry, not solute atom. Wait. Solute atom. Let's not write a solute atom. Let's write solute atoms. The stress field around solute atoms interact with stress fields around the dislocation. Around a dislocation and consequently hinder their motion. Right? This leads to strengthening. Now that we have come to strengthening, let's understand what are the factors that affect this solid solution strengthening, right? Factors affecting solid solution strengthening. Okay. First factor, which is a very obvious thing from the diagrams that we have drawn here, the size of the solute atom, right? Size of the solute atoms. So that will have a direct effect on the solid solution strengthening, because more the size difference, higher is the strengthening. Okay. Okay. Secondly, of course, elastic modulus of the solute, right? How strong the solute in itself is, right? So if the solute atom itself is very strong, then we will see that hindrance will be more, right? As an obvious thing. So elastic modulus of the solute atom so higher the modulus, higher is the strengthening, right? And third, solute concentration. So increase in solute concentration, of course, will increase the strengthening effect, right? We have already seen how solute concentration variation will change the strength. So solute concentration, of course, the last point. Increase in concentration, will lead to higher strengthening. Right? So these are the factors. One important thing to keep in mind, I'll probably write it as a note. One important thing that you have to keep in mind, that, okay, let's note down. There are two notes that probably you can keep in mind. Actually, not one but two. So first thing, we can't keep adding solute in the solvent, okay? So there is a solubility limit beyond which it will start forming second phase. So we go from solid solution strengthening to precipitate strengthening beyond a point, okay? So we can't keep adding. So there is a limit up to which we can keep adding. So that is something that you have to keep in mind. So let's write that down. We cannot keep adding solute in the solvent. Solute in the solvent as there is some solubility limit. As there is some solubility limit, after which it starts forming a second phase. Okay. Secondly, for the same size difference, okay, for the same size difference that we see, the smaller atoms will give greater strengthening effect. Okay, because you can accommodate more number of smaller atoms. Okay, essentially. So that's the basic idea. Therefore, if you have smaller atoms, they'll give more strengthening effect compared to larger atom for the same size difference. The smaller atoms give greater strengthening effect. And give, not gives. Okay, so these are two notes that you can keep in mind. Okay, uh, just a second before moving on. Yeah, okay. Sorry about that. Okay, yeah, coming back. So now that we saw what kind of distortions each kind of solute atom produces, let's see what kind of distortion fields are in a dislocation and how these different solute atoms can interact with this dislocation, particular dislocation. So let's see distortion in lattice due to dislocation. Okay. So first let's look at edge dislocation. Okay. So how does the distortion field look like, or the stress field looks like? Yes, so let's look at the stress field itself. For edge dislocation, it will look something like this. We'll have the XX, XY, and YY components. All the Z components except ZZ component will be 0. Right? This is how our edge dislocation looks like. So essentially, in edge, we will have both shear and tensile or compressive stress fields. Right? Right? So that is what we see in edge. While in screw, oh yeah, so since they are we are only talking about we are talking about both shear and tensile compressive stress fields. So we'll have both distortional, which is like shear, and dilational, which is like uh, tensile or compressive components. Okay, both distortional and dilational components. This is edge. And let's come to screw. So stress field for screw would look like all the components that the edge does not have, right? So all the component that edge has will become 0. But whatever edge does not have will become non-zero. So in screw, essentially we have only shear stress field and therefore only distortional component. Okay. So now that we know what kind of components we are seeing, can we like relate it back to whatever distortional field that we saw? So in interstitial, we saw kind of like a non-spherical distortion field, right? We saw like a longitudinal field. So we'll have distortional as well as dilational. it went in one direction. So it is having both dilational and distortion component. While in substitution, we are seeing a spherical kind of distortion field, right? So it is concentrated around it. So it is kind of only distortional. There is no dilational component to it. So if we put it in a table, let's say substitutional and interstitial. We're looking at edge and screw. Okay, so substitutional, since it has only like a spherical distortional component, we can say that it will only interact with edge, right? While screw, it might not be able to interact because there is no shearing happening, right? So that will not be there. While interstitial will interact with both edge and screw. Okay, so this is something that you can keep in mind. Just a second. So therefore, since interstitial atoms, solute atoms, are able to interact with both edge and screw dislocation, in any system we'll have dislocation which will have edge characteristics and screw characteristics, right? Because we'll not have like only edge or only screw happening in any system, right? We'll have a component of both. And since interstitial are able to interact with both, they will give a higher hardening effect, right? Because they can interact with more number of dislocations, right? So therefore we can write interstitial solute atoms interstitial solute atoms will give higher hardening effect Okay, interstitial solid solution will give higher hardening effect as compared to substitution atoms. Okay, everything per unit concentration, of course, like for the same amount of concentration. We're comparing them. Okay. So, where would these atoms typically go and sit? The solid atom, if they are going and interacting in dislocation, where are they essentially going and sitting? So let's look at it from the perspective of what happens in and around a dislocation. Okay, so let's add a few more pages. Okay. So let's say I have this setup. Okay, 2, 3, 4, 5, 6. Then 1, 2, 3, 4, 5, 6. The next one we have one less atom. Okay, so we have something like 1, 2, 3, 4, 5. So we are essentially having a dislocation here. Let me use a different pen. So beyond this, all the other layers I also have. So I'm looking at edge dislocation. Okay, we are having a dislocation present here. Now, what is happening in and around dislocation? Now, if this is my dislocation, what kind of fields will I be seeing? So on top, there are more atoms. So let's see, around the dislocation, I'm trying to draw the fields that we'll see. We'll be seeing this around this edge dislocation. Okay. So on top, we are having more atoms, right? So essentially, because there are more atoms, they will try to compress to accommodate for that shape difference. So it will be compression here. We have already discussed this, what kind of fields we'll be seeing, but just again, we'll just revise it. Bottom will have tension because there are less atoms. And from top, we are getting a pressure to expand, right? Because they have 6 atoms while bottom has 5. So the top half will exert a force to expand. While on the sides, we'll be seeing only shear, right? On the sides, we'll be seeing only shear. So essentially, with this in mind, where we have compression, tension, and all, where will each atom go and sit? Now, if a substitutional atom which is larger than the solvent, if it is larger, where would it want to go and sit? It will try to release the tension, right? Because it is larger, it can release the tension. So it will try to go and sit below. So we can say, if I use a red ink to probably draw this, a substitutional atom larger than the solvent atom. Okay. So consequently, where would a smaller atom go and sit? It will try to go and sit above, right? So smaller atom will go and sit in the compression region. So here we can see a substitutional atom smaller than solvent. So this is the basic thing about substitutional atoms. Now, where will the interstitial atom go and sit? Let me use another ink. The interstitial atom would tend to go and sit below, right? Below the dislocation, because that's where the tension is. So to try to fill in that tensile gap. So it will go and sit somewhere here. So this is my interstitial atom. Right? So you can see where each individual atom can go and sit, like what is the location. So essentially what have we learned? Like interstitial atoms will probably go and sit below the dislocation line. Interstitial atom mostly go below the dislocation line, right? Because most of the times they want to release the tension. While the substitutional atoms, they go above or below depending on what is the size of the substitutional atom, okay, whether it's big or small compared to the solvent atom. Okay. Now, why are we doing this whole exercise? Like, why are we thinking where it will go and set and all that? Essentially, impurity atoms, right? They are getting attracted to this dislocation. Why? Because they also have stress field around it, and the dislocation also has stress field around it. So this impurity atom will kind of tend to get attracted to this dislocation to reduce the overall strain energy that is present in the lattice. Okay. So it to reduce this, they are trying to get like accommodate themselves around the dislocation in such a way that the strain energy will get reduced. But because they get fixed, right? Because now the dislocation and this impurity atom kind of gets fixed to each other as they've reduced the strain energy. Now, if you want to move the dislocation, you have to put in an extra effort. Okay, and that leads to something very special. Okay, so let's come to carbon or nitrogen in steel. Okay, so there is something known as Cottrell atmosphere. Let me just take this one in. Yeah. So, like we saw, right, interstitial atoms tend to get like go to the dislocation and get accumulated around the dislocation, right? So, if this is my dislocation line, so what will happen is the impurity atoms will come and they will just sit around it. Okay, they'll just sit there. Okay, now because now these impurity atoms have gotten fixed, or I'm saying particular, so I'm saying carbon or nitrogen atoms. Let's take a specific example in steel, because this is most commonly observed in steel only. Let's take that example. So this carbon or nitrogen atoms in steel will kind of go and sit around the dislocation. Okay, and since these are interstitial atoms, like not substitutional atoms, they are interstitial atoms. They will kind of go and sit below the dislocation line. Okay. Now, what happens when dislocation tries to move? Initially, there will be like a huge resistance because the entire region is filled up with these impurity atoms, right? So, when yielding starts, right? So, essentially, like for normal, like all other systems, you will generally see stress versus strain curve, something like this. You'll see like this, right? This is a general stress versus strain. But in steel, what will happen is when yielding starts, right, because of the presence of this carbon or nitrogen, initially you will have to supply an extra, let's draw this here, an extra energy. Okay. Now this extra energy, right, this upper yield point and lower yield point is what we are defining happening due to this presence of this carbon or nitrogen. Okay, so that initial extra push has to be given because those there is an atmosphere which is formed around a dislocation known as Cottrell atmosphere. Okay, now what is happening is this set of favorably oriented grains, okay, they will sit together and they will like essentially not allow plastic straining to take place. Okay, so you have to keep pushing the dislocation beyond a point after which the plastic deformation will start. Okay, so you have to give this extra y upper, you have to give this extra stress to move the dislocation initially. Okay, so once that happens, now once the dislocation starts moving, this Cottrell atmosphere breaks down. Okay, and once it breaks down, then the stress falls down below to the normal level. Okay, so that falling down is what you are seeing here with the lower yield point. Okay, so it breaks down and falls to the lower yield point, and then yielding goes on according to how yielding should normally go on. Okay, so that's why you see an upper and lower yield point in steels, which you do not commonly see in other material systems. So even in cast iron, you don't see that, right? You see it in steel, but not in cast iron. So you can understand why that is so. Because of the presence of carbon, you are seeing that like presence of like you're seeing that quadral atmosphere being formed. So you have, in order to circumvent that, to pass through that quadral atmosphere, you have to apply an extra amount of plastic deformation, which will ensure that this dislocation bursts through this like quadral atmosphere, and once they burst through that, then the dislocation can flow slowly and the yield stress holds down. Okay, so that is what is about quadral atmosphere. We can go, like, I don't want to go in detail essentially because it's not something that is directly part of your syllabus, but I just wanted to discuss it. Okay, so one important thing that you have to note down is the strain rate, okay, associated with any dislocation. Okay, so this is something that you have to note down because it's an important formula. Then that also defines quadral atmosphere, but more importantly, it defines any dislocation strain rate. Okay, so you have to define strain rate as B times rho times V. Okay, B rho V, where B is the Burgers vector, right? Rho is the dislocation density. And V is velocity of dislocation. Okay. So you can remember this equation. Essentially, from this equation, what we can see is V is proportional to the shear stress, right? Because shear stress is proportional to the strain rate. So V is proportional to the shear stress. So as V decreases, the shear stress will decrease. Okay, or as dislocation density increases, V decreases and shear stress will decrease. Okay, for a constant strain rate. So that is something that you can keep in mind. Okay. So with that, we'll come to an end to solid solution strengthening. Let's move to the second type of strengthening for today, that is grain boundary strengthening. Okay, let's quickly learn about that. Okay. So again, like normal, the strengthening effect that we observe due to hindrance in dislocation motion caused by the presence of grain boundary is grain boundary strengthening. I'll not write that down. Okay, just we know like what grain boundary strengthening is, right? Just like how solid solution strengthening or precipitate strengthening. The strengthening effect caused due to the presence of grain boundary which hinders the dislocation motion. That is grain boundary strengthening. Okay. Now, why are we essentially seeing this kind of strengthening? Because you will have like grains oriented at different angles, right? So if you have a grain which is oriented at a particular angle, let's say like this. Now, you might find that some other grain might be oriented at a different angle, like this. Right, and because of this grain 1 and grain 2 will have some sort of misorientation, and dislocation cannot easily flow to this next grain. So there's a hindrance in dislocation motion. Okay. So that is what is grain. Because of orientation change, the dislocation directly cannot flow to the grain 2, and therefore you will see that hindrance. Okay. So why does the strengthening occur in grain boundary strengthening? There are two major reasons. Okay. First things. All right, let's write it down actually. Just a second. Yes, sorry. Okay. So yeah, coming back to strengthening. So why does the strengthening occur in grain boundary strengthening? Essentially, so there are two reasons. A, the dislocation passing from grain 2 to grain 1 will have to change its direction of motion, okay, due to crystallographic misorientation, right? Because grain 2 has a different orientation as compared to grain 1. There is some sort of misorientation, and the dislocation will suddenly have to change its direction, okay? So, dislocation passing from grain 1 to grain 2 will have to change its direction of motion. Okay, due to crystallographic misorientation. So that is something that you have to keep in mind. Due to crystallographic misorientation. Now, second point due to which strengthening occurs is because there is some sort of atomic disorder that will be introduced at the grain boundary, right? Because the grain boundary region is like two different grains at different angle coming and meeting. So there will be some sort of atomic disorder at that region where grain boundary is. So there is some discontinuity in the slip plane from one grain to another, which will also lead to some hindrance for dislocation motion. Okay. So atomic disorder within grain boundary region. Will result in discontinuity of slip plane. Continuity of slip plane. Discontinuity of slip plane from one grain to another. Okay. So these are the two reasons why strengthening will occur. Right. So at the grain boundary region, you will have some sort of atomic disorder, which will not allow dislocation to pass through easily. Secondly, there is a change in angle due to orientation differences between grain 1 and grain 2. So dislocation has to slip from one angle to the next angle, and then it has to suddenly move. So that is probably not very easy for dislocation to do. Okay. So due to this, what will happen essentially is you will see a pileup of dislocations at the grain boundary. Okay. Okay. So they will. So essentially, the dislocation will start piling up at the grain boundary in some sort of fashion. Okay. So what will happen is, supposedly this is my grain boundary. Dislocation will come. First dislocation will come and sit here. Okay. Now, because one dislocation is already present, the next dislocation will be like because it's a light dislocation. The next dislocation which is coming in is a light dislocation. It will face some sort of repulsion due to the presence of first dislocation. Okay, so there is some sort of x1 which will be introduced. Then the very next dislocation will also face some another x2 repulsion. Okay. And then the next dislocation will face x3. Okay, so essentially your x1 will be lower than x2, which will be lower than x3. So as dislocations start piling up over time, you will see that each dislocation will be further and further away. Okay, because of this repulsion. Okay, so all these dislocations are being acted upon by this shear stress tau, which is forcing them towards the grain boundary, and they are being repelled out. Okay, so let's first write down the force on each dislocation. Okay, so it is given by, due to this repulsion between dislocation, the force on each dislocation is given by this equation: gb square by 2 pi 1 minus nu x times x square minus y square divided by x square plus y square the whole square. Right? Now if there is no like y, like all of them are having equal y, so then we can just cancel y, make y 0, so it will become gb square divided by 2 pi 1 minus nu x. Right? So essentially what is happening is each dislocation in this pileup is under equilibrium due to the effect of applied stress tau and stress due to the dislocations in the pileup. Okay, stress between the dislocation, the repulsion that they are having in between each other. So each dislocation in the pileup is under equilibrium. Under equilibrium. So E, it is being acted upon by effect of applied stress tau. And B, stress due to other dislocations in the pileup. So essentially what is happening? These two stresses are kind of balancing each other out and they are in equilibrium. Okay. So the resulting force that is acting on the dislocation can be found out using this equation. So let's just write down, I'll just write down the final version. Therefore, the resulting force acting on the ith dislocation is given by so there's a equation tau minus sigma from j is equal to 0 to n, okay, where I is not equal to j. Okay, you can write gb square by 2 pi 1 minus nu into 1 by xi minus xj. This should be equal to 0. So by balancing this equation, we can find the force. on the ith dislocation. Okay. Uh, so due to this pile up, there is a stress concentration. Okay, at the junction where the dislocation and grain boundary are existing, right? So at the initial junction, there will be a huge stress concentration, right? So this will lead to high stress concentration uh, at the junction, right? Where the first dislocation is present essentially. So at the junction, there will be high stress concentration. So because of this, because of this, yielding can occur on the other side of the grain boundary. Okay. Society as GB. Okay. So essentially, what is happening is we are seeing a nucleation of dislocations. Okay. And yielding is occurring on the other side of the grain boundary. So we'll see a nucleation of dislocation. However, what will happen is sometimes instead of yielding occurring, you will see a nucleation of crack at the grain boundary. So there is a crack that will suddenly initiate at the grain boundary due to this high stress concentration. So sometimes this can lead to cracking as well. However, sometimes nucleation of crack at the grain boundary can also occur. Okay, so this is something that you can remember. So, if if you want to represent what is this stress, like this high stress concentration that is happening at the junction, right? If you want to represent, what equation do we use? So there is an equation given by tau star is equal to n times tau alpha, tau a, sorry, where n is number of dislocations in a pile. Okay, tau star is stress at the leading dislocation. First of all, first leading dislocation. N is number of dislocations in a pile. Number of dislocations in a pile. Okay. While tau A is applied resolved shear stress. Okay. So this equation will basically give us an idea of what kind of stress is present at the leading diagonal, which can lead to this high stress concentration and basically yielding, right? So if you want to get a figure, so we can get it using that. So if we rewrite and like turn this equation around, finally we can get number of dislocations number of dislocations in a pileup. Number of dislocations in a pileup to be equal to n equal to L times pi tau A divided by alpha G. Okay. Tau A is the resolved shear stress, applied resolved shear stress. I've already said that. Alpha is a geometrical constant. Okay. It is like 1 for screw, 1 minus nu for h. Okay. So it is like a geometrical constant that you take for screw or h. B is the Burgers vector. L is the length of the pileup. What is the length of the pileup? Okay. So, when the source lies at the center of the grain, when the source lies at the center of grain, I can write L to be equal to d by 2. So, d is like the diameter of the grain, d by 2. Okay. So, I can rearrange and rewrite this equation as d by 2 equal to n alpha GB divided by pi times tau A. Okay. So, let's say that the critical stress required to overcome the critical stress that is required to overcome the grain boundary obstacle, let's represent it by tau C. Okay. Let's take a quantity known as tau C, which is the critical stress required to overcome grain boundary obstacle. Okay. So, if we go back to our initial equation, tau star is equal to n into tau A, we can just rewrite that as your n into tau A should be greater than or equal to tau C at least. So, for that, so that the dislocations are able to traverse the grain boundary and move through. Okay. So, if I rewrite for n, d by 2 pi tau A divided by alpha GB should be okay. So tau A into tau A. So this will become one more tau A into tau A. Should be greater than tau C. Greater or equal to tau C. Or tau A should be greater than or equal to 2 alpha GB tau C divided by pi whole under root, okay, into d to the power half or minus half. Okay, so I can rewrite that as tau A should be greater than or equal to tau naught plus k times d to the power minus half. Okay, where k is basically representing this portion. this is K. Okay, and tau naught is the stress needed to friction stress needed to move the dislocation. Okay, so it is added due to the friction stress which is present. So friction stress needed to move the dislocation. Okay, so this is my final expression, and this is commonly known as. Let me just add one more page. I think I'll be done after that. This is commonly known as Hall-Petch theory or Hall-Petch relation. Okay, which is sigma y is equal to sigma naught plus k divided by root of d. Okay. Okay. So as d decreases, your sigma y will increase. Okay. So yield strength. So if we are rewriting this entire thing, this is the yield strength of polycrystalline material. Of course, tau naught is my friction stress. D is the grain size. So, what is the direct correlation that we can see here immediately? That with decrease in grain size, we'll see an increase in the yield strength, or more number of grains. If you are creating more number of grains, we'll see an increase in yield strength, right? So there is a lot of push towards these nanomaterials, right? The idea behind that is same, right? If you increase the number of grains, if you decrease the grain size and increase the number of grains, we'll see an increase in the yield strength. So that is the basic idea. So if we write this, or if we plot this, let's first plot it. This will look something like this: sigma y versus 1 by root d. If I'm plotting, it will look like this, where this is slope is given by k. Okay, and this is by sigma naught. Okay. So what does Hall-Petch theory exactly say? It is saying that postulates that dislocations can burst through the grain boundary. Okay, and it is valid for large number of dislocations in the pylon. Okay. However, this theory was kind of not agreed upon by Cottrell. Okay, so Cottrell gave a different kind of theory. So let's just look at it quickly. Cottrell said that it is virtually impossible for dislocation to burst through grain boundaries. Okay. to burst through grain boundaries. Okay. So what Cottrell said was, the stress concentration produced by pile-up in one grain activates dislocation source in the adjacent grain. Okay. So this is the basic premise of Cottrell's theory. The stress concentration produced by pile-up in one grain activates dislocation source in the adjacent. Okay. So Cottrell's equation was a little bit different. It looked something like this. Tau A is greater than or equal to. It had the same premise, tau naught, but the equation, the second half of the equation looked a little bit different. It has 2 tau C, uh, 2 tau C, let me see, yeah, lambda to the power half and d to the power minus half. So this was Cottrell's equation. Okay. So again, this is not very important to know, but like it's not very important to like remember the equation, but essentially this is how the equation looked. Okay, Cottrell's equation. So with that, we're coming to the end of theory. Let's move on to some problems. Okay. The first question is, which of the following are true? Matrix and precipitate must have same crystal structure. That is wrong. Solute is an atom, but precipitate is a phase. That is correct. As concentration of solute increases, it leads to increase in solid solution strengthening. Again correct. And matrix and precipitates may not have the same crystal structure. Again correct. So second, third, and fourth options are correct. Okay. Second question: which of the following statements are correct? Interstitial atom leads to non-symmetrical stress field. Yes, that is true. It is non-symmetrical. It's not spherical. It's non-symmetrical. A large substitutional solute atom leads to non-spherical stress field. That is wrong. Substitutional atom will always lead to spherical stress field. So third option, a small substitutional solute atom leads to spherical stress field, is correct. Fourth option, substitutional solute atom leads to spherical stress field irrespective of their size with respect to solvent atoms. That is correct. It will always lead to spherical stress field. Next, factors affecting solid solution strengthening are elastic modulus of solute atom, of course. Size of solute atom with respect to solvent, of course. Concentration of solute atom, that is also there. Whether the solute atom is substitutional or interstitial also will affect. Okay. Now coming to the fourth question. Which of the following statements again are correct? First one, substitutional atoms interact with both edge and screw, that is wrong. Interstitial atoms interact with both edge and screw, that is right. Interstitial solid atoms lead to higher strengthening effect than substitutional solid atoms, that is true. Substitutional atoms interact with only edge dislocation, again true. So kind of like all these theories what we have studied, like we are seeing it as in a problem form. So which of the following statement are correct with respect to solute atom interaction with the dislocation? Okay. So smaller substitutional atoms are attracted towards the compressed region of the lattice, correct? Smaller ones are attracted to the compression region. Larger substitutional atoms are attracted towards the compressed region, that is wrong. Larger substitutional atoms are attracted towards the tensile region, that is right. And impurity atoms are attracted to dislocation to reduce the overall strain energy, that is also correct. Okay, so next problem is a question, like it's a problem given to us. If the magnitude of Burger's vector is 3 angstroms, dislocation density is 10 to the power 8 per meter square, and strain rate is 9 into 10 power minus 7 per second, then what is the dislocation velocity in meter per second? So we already have the equation, right? Epsilon dot is equal to B rho V, right? That is the equation. So epsilon dot is given to us strain rate 9 into 10 power minus 7, right? B is given to us 3 Armstrong, and let's convert it into like SI. So 3 into 10 power minus 10. Rho is given to us 10 power minus 8, say 10 power 8 meters per meter square. So 10 power 8 per meter square. V is what you have to find out. So let's calculate V. Just use my calculator. So 3 into 10 power minus 5 is what I'm getting, meter per second. So third option is right. Okay. So moving on. The strengthening mechanisms that will be observed in steels is our solid solution strengthening, of course we can see that. Precipitation strengthening also we can see that. Grain size strengthening also we can see that. So all of the above. The reduction in grain size generally improves. What does it improve? The reduction in grain size. It will definitely improve the hardness, right? Creep strength, no, that is not related to grain size. Room temperature strength will be improved, of course. Young's modulus, again, it's something that is related to the material, not grain size, so that will not be improved. Okay, next again we have a problem. For an alloy, the yield stress is 240 megapascals when the grain size is 144 micrometer. What would be the yield strength of the alloy in MPa when the grain size is 100 micrometer? Given the frictional stress of the alloy is 120 megapascals. So they have given us a lot of quantities. They have given us what is the yield stress. They have given us the grain size. They have given us the friction strength. Friction stress they have given, and they are asking us what is the yield strength when the grain size is 100 micrometers. So the new grain size we have to find. For the new grain size we have to find the yield strength. Okay. So foremost we have to use sigma y is equal to sigma naught plus k times d to the power minus half. That is the general relation, right? So given to us 240 as the yield. Sigma naught is given as 120 plus k is given as, k is not given, so k is what you have to find first, and this is given as 144 into 10 power minus 6. So this will give us k equal to something. Okay. So once we find that k, we can substitute it back to the next second half, which is sigma y2, some y2 which you have to find, which is 120 plus some k into 100 into 10 power minus 6. Okay. So this is to the power minus 6. So let me first find the k value. Can we calculate the whole thing? So let me just calculate. So I'm getting 1.44 into 1.44 only. Yeah, that's direct. 1.44 MPa per MPa meter to the power half. So let me just rewrite this. Okay. Now using this, we can substitute it back 1.44 into 100 into 10 power minus 6, right, to the power minus half to get our new yield strength value, which is, let me just calculate the value for you. Yeah, so the final answer I'm getting is 264 MP. Okay, just a second. Let's check it again. Some of the options are not matching, so Yeah, I think the options are incorrect. It is supposed to be 264 only. So I think my calculations are not wrong. So 264 MPa is the final answer. The options are incorrect. So yeah, so this is the final answer. Okay, so coming to the final question of the day. Which of the following statements these are correct? Dislocations piled up against the grain boundary may initiate cracks at the grain boundary or yielding may occur at the grain. That is correct. Dislocations piled up against the grain boundary produces a backstress to oppose motion of the incoming dislocation, also correct. As we move away from the grain boundary, distance between the dislocation increases. That is also correct. And dislocation near grain boundary can easily traverse to the other grain. That is wrong. So this is dislocation. Okay. So I hope everyone was clear on all the problems that we have discussed, everything that we have discussed today. All the theory, everything that we have discussed, everyone has no doubts. I hope that is clear. So in any case, if there are any doubts, any questions, we can always discuss that in the upcoming sessions. So with that, we will end today's session. I thank everyone for attending and we'll meet again in the next session. Thank you.